We have minus sometimes, around plus minus something. Can be rainy also some days. Yeah.
Okay. Doesn't sound too bad though. It sounds a lot like Pennsylvania. It's about 0 right now, or 0 Celsius here.
Did you? I located the JavaScript solver. I think that's the best one to rewrite in this case. I post it on the Facebook now.
Okay.
So a bit down on that page, you find it. It sticks out a little. This was, I guess, this was the one being shown some slides previous today. But if we change the equations, there has to be some redesign on, and I'm not really good at that to disturbance step with.
Are you speaking to me, David?
You need to be some kind of numerical analyst. You know how to step time in this case. If it's too coarse, then the precision will go down, and even if it's too small, precision can also be hurt.
I was thinking of doing, well, the adjustment that I was making. I was thinking of doing that in Mathematica, because that's only it's not very big program, and
yeah, I just, the two latest links I post on Facebook are one JavaScript and one Mathematica link. But I haven't checked, but I guess they are the same software, aren't they?
Mm-hmm. Did you see the link I put on rotational diffusion?
Well, rotational viscosity I've been investigating since some years, a little now and then. Rotational diffusion, is it related to that?
It's a version of Flick's law. It's an adjustment of Flick's law for rotation instead of just translational diffusion. It's rotational diffusion. So that's another possibility.
Yeah.
I mean,
I saw it just quickly. Maybe I didn't get the point or the yeah.
I was thinking of looking at it very simply.
That's understandable.
I was trying to look at it very simply, just get down to the very basics of what's going on, and think, if I look at what someone else is trying to do, they've developed it a lot, and it looks quite complicated. But when I think of it for myself, trying to understand what's going on myself, then that simplifies it a lot. You're starting with the very basics, like if you've got rotation, if you've got translational motion and rotational motion, then if you include, if there's no rotation, then the angular component's going to be 0, and then they will just have translation. So the angular part accounts for both the angular and the translational part. So what I was trying to do is get back to it and think about it in very simple terms, very basic terms, what Paul Laviolette's done with the derivation of diffusion, and try and include a rotational. And that could involve either fluid rotation or possibly even fluid vortices. I've got to put a video up on that.
That would be the least complex approach.
Just think about it on the very basic terms, what's actually going on. Because when you understand it for yourself, it's simplified. If you try and understand what someone else has done, they've done a lot of work, they've developed it a lot, and it just looks like a horrific mathematics. But then you say, well, what do I really understand? How can I understand it myself, what's going on, instead of following what someone else is saying? When you try and understand it for yourself, then you get back down to the basic building blocks, and it becomes much more simplified. That was my experience when I was doing my PhD, looking up papers on tomography, and it's very complicated. Someone spent a lot of time and they developed it to a high level. It looks very complicated, but when you try and understand it for yourself, what's really going on, that simplifies the whole thing, and you arrive at an answer you're looking for.
Could you explain the how the radial diffusion arises a little bit more? Like what precipitates radial diffusion?
Okay, let me just share this.
So you need radial radial diffusion.
I mean rotational, excuse me.
Rotational would require gradients that are perpendicular to the radius. In other words, tangential gradients.
Right.
All the way around. And right now, there's nothing that would cause that to happen in the model.
Is that what you're thinking, Brendan?
So that's why I was thinking of adding this term here. Can you see this? This is
Yeah.
the diffusive constant and the rate of change of diffusion with respect to space. Then Paul's added this term in here to be moving relative to another reference frame of a velocity VO. So I'm then saying, well, why don't we add another component, which is the rotational component? So this dV by dr is the rotation, multiplied by delta r, that puts it into the units of velocity. And then times the
It's a concentration.
So I'm just playing around with it. I'm just kind of playing around with it at the moment. But in that video I showed you when he was talking about rotational fluid rotation in the very introduction to it, he's got a term for velocity here, and then he said, okay, so the system is moved. Say the system is moving, then you add this term here, and you get the rotation of the fluid. So I'll show you where he put where I got the idea from. I got the idea from, if I can find it. Okay. Oopsie. Don't want that. Stop share. Share. Here we go.
I take it that essentially you'd be creating a rotation mathematically, but
a rotation term. So if there's no rotation, then if there's no rotation, then it's just linear. It's just linear radial diffusion. But if there's rotation, then but when there's rotation, there's also linear. There could be, if the linear part is 0, then there could be then the rotational part will come in. But if there's no rotation, then there'll just be the linear part. So you could put into the model, you could say, like in Brownian motion is random. So some of these random processes have random angular motion. Some of them don't. Some of them are linear. So let me just see what here it is here.
Essentially, you're kind of proposing just it's like some coming up and spinning it, and then modeling that mathematically.
So here, this one here, can you see that? This one here is what Paul had originally. So you've got linear diffusion, linear radial. Then I'm suggesting we put in a component for rotational. Now, if I can find it here, well, I'll show you where I got the thing from. Here. Actually, here it is here. So here you can see. So he's describing fluid rotation here from the very basics. He's saying the rotation of a fluid can be explained by omega, the x and y and z components of omega. Then he's showing here an object, say a box, which is what. Just turn that off.
It's not like coast to coast.
He's showing the rotation. He's then taking the component, he's looking at the components of the rotation of that square and he's doing it in the Z, so he's doing rotation around the Z axis. And can you see here, he starts with say at the origin, we've got V at the origin equals the value of velocity. And then he's saying at A, this is point A here, and this is point B here. Then at A, you've got the translational velocity, and then you add the rotational. So dV by dt by dx is rotational motion multiplied by delta x, puts it into the terms of velocity, so that you then got it as a velocity component, but it's radial velocity. So here's a translational velocity, and then he's working out components for omega OA at one point.
Does this rotational diffusion cause a torque on the particle?
Yeah, so that's the point I'm right. So now stop share, do share. So let's have a look. Okay, so this is what I've done here, is to look at. So I've then said, okay, so we've got Flick's law, diffusive constant multiplied by the rate of change of concentration of etherons. Then it's moving relative to, if it's moving in a relative frame of reference to something else, then it's velocity times concentration. That's what Paul put it in originally. So I'm saying now add another term, which is the rotation. So if there's no, say there was no rotation, then this term would be 0. But if there is rotation, so this is just my thinking of it at the moment. So you've got a term for this. Now I'm trying to think of it very simply. So we've got a term so we've got a system of diffusion at a boundary. It's moving with a velocity v, translational velocity, and it's also moving relative to in a rotational frame here. So if this is the correct formula, or if this is one of the correct formulas, all you have to do is just adapt model G to include these terms here. Because Paul's taken this term out in the Subquantum Kinetics book. He's saying it's not necessary. So if we could adapt model G to include these two terms, one for translational motion and one for rotational motion. So obviously the translational motion is moving, from what I understand, unless I need to go back to this one and change this here. I'm not sure if I think I could keep that. So you've got one part has translational motion, and that's changing. And then another part's got a rotational component, that's also changing. So, okay, so that's one. So this might work. I'll stop the share. So, and then I'll go back to this one here that I had. So here's another one. Whoopsie, I want that. Yeah. Here's another one here, which is here, rotational diffusion. Can you see that?
Yes.
So I go to that one.
Rotational
diffusion. So it's got another. So remember, Paul used Flick's law to define diffusive flux, which later went into model G. Here you've got rotational version of Flick's law. So it might be that the other one I've said might be okay. It might not be. But if this is another thing we could try, is showing the F is the probability density function. A rotational version of Flick's law can be defined. So it's this term here.
Okay.
There you see the rotational diffusion constant there. But I wasn't quite sure when I was reading this. It was talking about let each rotating molecule be associated with vector n. I was thinking, is the molecule? I thought it was the molecules were in rotation around I thought that might be a typo. He might have got that wrong. So he's talking about here about the molecule rotating in diffusion, but I think it means the concentration, the concentrational fluid rotating. So that might be a typo. because it doesn't make sense. It doesn't quite make sense. It might be right, it might be wrong, I'm not sure, but it doesn't quite make sense to me. Rotational diffusion is when the fluid is rotating, whereas this seems to, he seems to be saying here a rotating molecule. So this was the other one, the other basic rotational diffusion, but you can see they involve temperature and Maxwell Boltzmann's constant there. So that's involving temperature. This one here, you don't, with Flick's law, you don't have to involve temperature.
That's nice.
So I was writing up a document at the moment. I can send it out to people when I've finished, of just trying looking at these different ideas and seeing if I can trying to investigate it further to see if I can find something that makes sense.
By the way, physicists have been modeling spin with vortical motion of quarks, it seems. Have you looked into that to see what they're doing?
No, I haven't heard of that. I'll check that out. That's interesting.
No, I haven't checked.
Quarks and simulating rotation in Google and came up with some hits.
Because this is
If you want, I can show you my screen here. Let's see.
Okay, I'll stop sharing. So I'll stop that share. Okay.
It says you cannot start screen sharing while others participant is sharing.
I've stopped my screen share, so it should be. Just stop it and restart it again.
Should I share now?
Yeah.
Okay. Can you see my? No, you can't.
Just stop the share and start it again.
Okay. Okay. Do you see this?
I can see it.
This is the the search I did. Quark simulation rotation.
So that could be interesting. So if they've been doing some modeling, that could help us.
Yeah. Yeah, we don't want to reinvent the wheel. So that might be something to check out.
Yeah.
So I guess I can stop the sharing.
I found in my PhD work that when I tried to understand when I was following what someone else was saying, I often found it quite difficult because they had developed it a lot. When I sat back and tried to understand myself what was really going on in my own ideas, that's usually when I solved the problem.
Well, that's because that's the way the mind is supposed to work.
Yeah.
It doesn't work well when somebody's teaching you.
Yeah.
It works best when you're learning yourself. It's a spontaneous connection with your own feelings. Yeah. So, okay. So anything else? Is there a need for funding of the work at this point?
No.
Well, for the interaction simulation, being that David has a computer, that it should be sufficient. So we shouldn't have to rely on outside computing resources or buying additional hardware. So unless, but maybe down the road we'll find that the acceleration may be very slight, and it may take more time to get to that point to where we can measure an acceleration, but we don't know that at this point.
Yeah. Okay. Anything else to discuss at this point?
Yeah, go ahead, Brendan.
I've got things I'm working on, like what I said earlier. That's what I'm working on at the moment. So I've had a look at the open foam, and I was working to a certain extent on that as well. I'm thinking what I'm thinking at the moment is the Mathematica program that produced those kind of graphs of 1, 2, and 3D concentrations. I'm thinking that if I can work out this rotational motion and add it to model G, then I could use the Mathematica to produce the resultant. And also work on OpenFOAM as well and try and set that up, because that's more similar to the ETD stepper C++ code. So that's another thing I can work on as well. I can't think of any funds that I need at the moment, no.
I was just wondering, David, did you want to get together sometime later this week, maybe, or maybe like a Zoom or something else, or just email and discuss this more? Work out the details?
Yeah, or maybe. I'm a bit busy, but at the earliest on Wednesday or Thursday, say Thursday then.
Okay. Yeah, feel free to contact me. Yeah.
Yeah.
I'm usually free. My availability is pretty good on Thursdays and Fridays.
Okay. Yeah. Good.
All right.
So, Paul, what did you think of that idea I had of adding the rotational component to the diffusive flux, total diffusive flux? Does that sound?
Yeah, it sounds reasonable.
It's just something I need to try and try it out, see how far I can get with it, or explore it more to see whether it holds water, whether it's concrete, whether it's got validity. I kind of like 3/4 understand it, so it's more of it's a bit of a guesswork, but it seems to make sense to a certain extent.
Yeah.
Yeah.
I'll go ahead and I'll wrap up I'll add some edits to that presentation, and I'll save it as a PDF, and I'll post it to maybe I'll send it out an email or include it in the meeting link on Facebook.
Okay.
Yeah.
Okay. So I guess we call the meeting to a close then.
Yep. Okay.
Yeah.
It's a good meeting with you all.
Well, we're making progress.
Sorry? What was that, Paul?
We're making progress.
Yeah, that's right. And also, I wonder what happened to Justin. May have been busy or something.
He forgot.
Yeah.
Or time zone difference. Who knows?
Yeah, send me a copy of the presentation, Michael. I'll be interested.
Okay. Then I'll just email.
Put it on Facebook or email.
Okay. Yeah. Yeah. Absolutely.
Okay.
Okay, guys.
Okay.
Cheers.
Yeah. See you.
Bye.
Bye.